I was discussing about the laser resonator. Simply, it is just consists of two mirrors facing each other, and we put light that travels through these from the faces of the mirrors, going back and forth all the time. And what it resonates is, in fact, the electric field of the light. And I was discussing that this shape, that let me draw also the zero line. This is the zero line for the electric field in the optical resonator. And the electric field magnitude, sorry, the electric field amplitude goes like this sinusoidal shape. And in time, this is going, this is just like vibrating string, okay? And I was discussing that, there were also the possible wavelengths for the light that can be put between these two mirrors, and we fixed the distance between the mirrors as L, okay? So the largest wavelength that you can put in order to call this a resonator or optical resonator is going to be just twice the distance between the mirrors. And I hope you understand why this is so, okay? Because, when you look at the shape, it goes like this and it will go like down on the other side. It will end up at the point where twice the distance between the mirrors. And since if this is the one wavelength, this is going to be half of the wavelength. So a wavelength is going to be just twice the value of the distance. And we have this conditions, boundary conditions, that, so to say, boundary conditions for the light in an optical resonator means that the light must have a zero amplitude in terms of its electric field at the location of the mirrors. Okay, so this is our condition. This is our only condition. But of course, you can always relate this wavelength to the frequency of the light by using this wavelength and multiply the frequency is equal to zero relation between the frequency and the wavelength. So this the largest wavelength is going to be the smallest frequency for the light that can be put between these two specific mirrors, which has a distance L. And it is going to be by this equation, C divided by 2L, okay? And for these kind of optical resonators, you may discuss about the losses. And the loss will be, of course, usually we think a ideal resonator, on which we have 100% reflective mirrors, but mirrors are not in real life 100% reflective. There is kind of losses in the surface of the mirror. Photons sometimes, even if very little, can be absorbed by the mirror, or sometimes the photons are just scattered off the way that they travel this direction, okay? So they are lost, okay? Since these losses are unavoidable, there will be losses, and the losses will appear in the frequency domain as the width of this signal, okay? So more you have losses, you have a wider this width in the frequency domain, okay? So this is how it goes for a passive light that travels between two mirrors. And this is the time domain, of course. Since there are losses, the amplitude will decay exponentially over time. Okay. So, you may have also discussed that, okay, just like in the case of a driving force for mechanical oscillators, can we drive this laser light so that we can compensate these losses? The answer is yes, of course. If it's now, we wouldn't have lasers working. We must have some driving force. Well, this will appear as we should feed the resonator by some energy, like maybe electricity, maybe some chemical reaction, etc. But most of the time, we will feed these optical oscillators by electricity. What we mean by feeding the oscillator by electricity means that we will create a driving force for the losses, and this driving force is going to be in the shape of a voltage, and this voltage is oscillating or alternating voltage, and this voltage is going to be provided by a driving power supply. And so you will have for all of lasers, for all of different types of lasers, you must always have these power supplies to run the laser. Okay, well, in the case of a laser pointer in your pocket, this is going to be just the battery, battery that you put in your uh, pointer laser. This is going to be the driving force for the laser oscillator. Okay, all right. Do you have any questions so far? I mean, if you can interrupt me if you want to make a comment or etc. All right. So what next? What next is that, okay, this of course this is not going to be only a possible wavelength that can live between two mirrors. You can also have this shape of uh, oscillating amplitude for the electric field. This shape is also possible. Okay, you can just fit one full wavelength for the amplitude of the electric field for the light between these two mirrors. By the way, we suppose that in each time we use only single wavelength light. Okay, so in this second picture, you may easily tell that the wavelength is going to be just L, because the distance between the mirrors is L. So the second possible resonance frequency or wavelength, so to say, is going to be just L. The first possible was 2L. The first allowed laser wavelength was 2L, and the associated frequency was C divided by 2L. And the second possible uh, resonance wavelength is L, and associated frequency is twice the first one, twice the smallest frequency. Okay, and you will see that this will go like two times, three times, four times, etc. It will go like a multiplication of a multiple integer. Okay, and we will fit more and more uh, wavelengths over here in between the mirrors. So if you see uh, more of the bumps inside the between the mirrors, that means you're increasing the frequency and you're decreasing the wavelength, of course. So this wavelength is smaller in compared to the previous one, but the frequency is larger in compared to the previous one. So how this should appear in the frequency domain? Well, the thing is that for this resonator, for this optical resonator, you can hold, that means so far, you can hold two different wavelengths or frequencies that can live in a single optical oscillator. And you can have this both at the same time, or you can have one at a time. Okay. And in this case, so far, you see that your oscillator has a multiple frequency or multiple wavelength. So how this will appear in the frequency domain is just this one. Every resonant frequency will appear as this bell shape in the frequency domain with some certain width, okay? And the difference between the central frequencies is going to be just C divided by 2L, because the second frequency is just C divided by 2L is larger than the previous frequency. And the other thing is that first frequency is just itself equal to C divided by 2L, okay? And you'll see that this frequency distance between these first two resonant frequency will continue, and you will see that you will continue to have the third frequency over here, the fourth frequency over here, etc. But all frequencies, resonant frequencies, will be separated by the same distance in the frequency domain, okay, which was this c divided by 2l. All right, is that okay so far? I hope this is fine so far. So as you might expect, this is the third uh, frequency, or third resonant wavelength, or third resonant frequency. So you see that it's just three times than the fundamental, three times larger than the fundamental frequency. This is called now fundamental frequency, and we always call the lowest frequency as to be the fundamental frequency of your optical oscillator or optical resonator, and the largest wavelength is going to be your fundamental wavelength. Okay, so it appears that it will go like this: two times, three times, four times, etc., and your wavelength will appear like 2l divided by n. So let me uh, write down a specific rule for the wavelength. For the nth resonant wavelength, it is going to be just 2l divided by n, where n is an integer, and for the associated frequency, it is going to be just n multiplied by c divided by 2l. Okay, so n is any integer, and all resonant frequencies will appear like, will go like this with by this n. Okay, so there was a special name about this frequency distance. I just forgot now, but I will remember anyway. Okay, this has a special name. All right. So uh, you know in fact, by this by this relation that you see, two mirrors can hold as many as you want the frequency, resonance frequency of light. But of course, you might ask, for the time being, that okay, you see all lasers as one single wavelength or one single frequency. Well, this is so, but this does not mean that the laser that you hold in your hand with a specific distance between the mirrors can only produce one single wavelength. It can produce many different wavelengths, but the medium between these mirrors, in fact, determines the wavelength, determines the specific wavelength, single wavelength for that specific laser. Okay. Normally, laser can hold many different frequencies, or the resonator for the laser. But of course, you will see that the two mirrors are not the only tools to build the laser. You will also have a light producing medium between the two mirrors. And this light producing medium, which is called the gain medium, will determine the single frequency of your laser. And we will come to this point later. All right. So, and this goes on and on. So, you might also, ask this question, that will this width for the losses be the same for all frequencies? Okay. The question is that, will this uh, width of all resonant frequencies be the same? Well, in general, it's not. Okay, in general, these widths are not the same, but they're close to each other anyway. So there will be some differences, and maybe we might discuss these differences later. Okay, for you might end up a larger width for going higher frequencies. Okay, and lower width. Sometimes it might be just the other way around. So this is, uh, I mean, this shape is not uh, does not represent the general case, that it appears that all of them just appears as the same height and the same width, but it's not the case for the general picture. All right. So just as an example, let's discuss that for a resonator of these mirror distances, which are 1 meters apart from each other. Okay, the fundamental wavelength is going to be just 0.5 micrometers. Okay, and sorry, sorry. For the for the laser, if you want to produce a laser of single wavelength, and you choose this laser to be 500 nanometers or zero point 0.5 micrometers, you want to find this integer n. I just put this integer n, this integer to be n, but over here this integer is appeared to be q. Anyway, q and n is just about the same. I mean, they're both integers. So for a resonator, optical resonator, which has the size of 1 meters, this is the distance between the mirrors. If you want to produce a laser of 500 nanometers or zero point 0.5 micrometers anyway, find this integer, okay? What is going to be this integer n for that specific wavelength? So you can find this just by solving this equation that you are given in the previous slides. You can find this q number or n number, the integer number, to be very high. It is for 4 millions, of course. I think it's 4 millions, yeah. It is 4 millions, okay? So until 4 millions, there are 4 millions of different resonant frequencies. Of course, it's not going to be the end. It will continue getting larger and larger value from this one in compared to this one. For that specific of wavelength, this integer number is just 4 million, 4 times 10 to 6. All right. And that corresponding frequency for the light frequency of that is just 600 terahertz, 6 times 10 to 14 hertz. So, in summary, to make an oscillator, okay, we need, well, in fact, this is not true. Anyway, to have a resonator, we must have an oscillator. And also, if you want to resonate your oscillator, you must have compensate these losses that I was trying to explain, that usually this is in case of a alternating voltage or alternating power supply for the case of a laser. Okay. All right. So is that end? I think this is the end for this slide. Yeah. All right. Do you have any questions so far? I hope you're not sleeping. Let me, by the way, open up the. Arkadaşlar orada mısınız? Sizden herhangi bir
Buradayım
şey.
hocam ben.
Buradayız hocam.
Tamam. Kendi kendime konuşuyor gibi oluyorum da. İngilizce de devam edebilirim, Türkçe de devam edebilirim. Yani bilmiyorum, İngilizce anlaşılır diye tahmin ediyorum.
Anlaşılıyor hocam bence.
Okay. So, for the records, let's keep English. And what next is that, I will discuss with you this new concept of light amplifier. So, I was discussing that you must have in between these two mirrors for the optical resonator, you must have means of some way to produce the light, yeah, because you will put light in from the external source, or if you want to produce the light yourself by the device itself. So then obviously you must put something between these two mirrors, and that something is called the amplifier, light amplifier. Sometimes it's called the gain medium, so the medium that produces light. Okay. All right, so we will discuss this, and then this is called usually a light amplifier. So what light amplifier is appears as that this region, this medium between the mirrors. Well, sometimes this medium might appear as a crystal, like a crystal. I mean, maybe diamond, like a solid, transparent, element that you can put, or this medium sometimes appears as a medium of gas atoms. Gas atoms also can produce light. Okay, sometimes it might be a liquid. So in the case of dye lasers, this amplifier is just a liquid, a dye liquid, boya. So I mean, this amplifier might come in physically many different ways. It's just a medium of atoms or molecules. So, but of course, it is able to produce light. I mean, that medium or amplifier must have this specific property that it must produces light. In somehow, if you give some energy to this medium, it is able to produce light. So this is we call optical amplifier. And what optical amplifier does is that it is just amplifies uh, a certain resonant frequency for that laser. For that laser, the frequency spectrum is determined by just the distance between the mirrors, and just by adjusting the distance between the mirrors, you just specify a frequency spectrum. But as I said, this medium is able to amplify or produce a certain wavelength light, a single frequency light. Okay, so that means when while the other frequencies dies out as time goes on because they have losses, eventually they will die out. But if you put this amplifier, a certain frequency that this amplifier will produce a certain frequency light will be amplified. Okay, because it produces light. That means it overcomes losses. It overcomes losses of some photons for each travel, let's say. If for each travel, let's say, if you just lose 10 photons, but if this amplifier produces 11 photons, then that means you just overcome the loss and you have gain. You have gain for 1 photon for every 10 photons. If this produces 11 photons for each travel, but the laser or mirrors are losing 10 photons for each travel, that means your optical amplifier just adds up to the power, 1 photon for each travel. Okay, if it would produce the same amount of photons that the laser or the resonator loses, then there will be nothing, any difference. Whatever the initial power of the light that you put, it will survive without changing its intensity, but it will not be amplified anyway. So it will be always the same power, the same number of photons that goes back and forth. Some of the photons will be just renewed because for each travel, some photons will be lost, but the new photons will come from the amplifier. So these photons will survive. The total number of photons will survive if there is no gain or if there is no amplification. But as I said, if this medium produces more photons than the losses, then you certainly have gain. So if you have gain, you see that there is another shape, a curved line like this. What this means that this specific optical amplifier is producing a certain frequencies of light between this value. Okay, this value I'm pointing over here just by tip of my marker, and this value. You see, there are many different frequencies uh, between these two points that the gain medium crosses the curve. This is the curve for the gain medium, crosses the horizontal axis. From this value on and to this value, this gain medium produces not only single frequency, but a range of frequencies between these two values. But between these two values, only one resonant frequency for the laser. There is only one resonant frequency of the laser. So that means that resonance frequency will survive. But you might ask yourself that what happens to the other photons that have other frequencies other than different than the this resonant frequency? What happens to those photons? Those photons which are produced by this amplifier will not survive because those photons having a frequency which is not the resonant frequency for this specific laser that have this certain distance between the mirrors. Let me explain this part in Turkish. Şimdi arkadaşlar dedik ki yani burada koyduğumuz amplifier ya da gain medium neyse birçok ismi var bunun. Sadece tek frekansta foton üretmiyor. Ürettiği foton frekansı range'i işte şuradan şuraya kadar değişiyor. Tabii ki bütün range'lerde de üretmiyor. Yani belli bir range'de üretiyor. Bunun ürettiği fotonların frekans range'i yani width'i bandwidth olarak düşünürsen bayağı geniş. Lazerin kendi rezonans frekans width'lerine göre bunun amplifier'ların ürettiği fotonların frekansı, bandwidth frekansı çok geniştir. Ama tabii yani sonuçta limited. Yani buradan şu frekanstan şu frekansa kadar foton üretiyor. Ama şunu da söyleyebiliriz. Peki ürettiği bu fotonlar ya da ışık e, bir saniye 10 dakika sonra kesilecek yayın. Evet. Ürettiği bu fotonlar her bir frekans için eşit sayıda mı foton üretiyor? Hayır. Bu zaten şu kör onu söylüyor. Mesela şu frekanstaki foton, şu ürettiği şu frekanstaki fotonun miktarı şuradan dik çizerseniz bu kadar. Ama mesela tam bu rezonatörün rezonans frekansında ürettiği fotonun miktarı bu kadar. Yani rezonans frekansında ürettiği foton miktarı şu frekansta ürettiği foton miktarına göre daha fazla. Yani bunun böyle bir kör olması aynı zamanda onu belirtiyor. E, fakat mesele şu ki bu rezonans frekansına gelene kadar ya da bunun bandwidth'ine gelene kadar şu üretilen fotonlar bu iki ayna arasında yaşamayacak. Yaşayamamasının sebebi şu. Bunların dalga boyları tam e, mirror'ların üzerinde yani aynaların üzerinde tam sıfırlanmıyor. Dalga boyları orada sıfırlanmıyorsa bunlar hemen sönümlenir. Yani bu fotonlar ürer fakat anında ya scatter olur ya sönümlenir, absorbe edilir. Bir şekilde birkaç tur bile tamamlayamaz. O yüzden eğer e, amplifier'ın ürettiği fotonların frekansı herhangi bir şekilde optik rezonatörün e, rezonant frekanslarına eş değilse amplifier'ın ürettiği fotonlar çok çabuk ölür, yok olur. Dolayısıyla amplifier ürettiği fotonların frekansı ya da ürettiği foton bandwidth'in içerisinde mutlaka lazerin bir rezonans frekansı olması lazım ki bu lazer bu özel rezonans frekansında ışık üretip dışarı çıkarsın. Bu arada tabii e, şunu da sorabilirdiniz. Yani madem içeride ışık böyle gidip geliyor, bu gidip gelen ışığı ben dışarı nasıl taşıyacağım? Yani nasıl kullanacağım? E, mutlaka göreceksiniz ki bu aynalardan bir tanesi yarı geçirgen olmak zorunda. Diğer türlü bu aynadan bir tanesi geçirgen olmasa zaten içeride üretilen ışığı dışarı taşıyamazsın. Yani kullanamazsın. Çünkü bizim kullandığımız lazer ve aynalardan bir tanesinin dışına giden, taşan veya geçen fotonlar. So one of these mirrors must be less than 100% reflective. Usually it is like 70% reflective, only 30% of the light will pass through. So whenever you are using a laser, only very certain small portion of the photons are coming out, and you are using these output photons as the laser, okay? Usually in between the mirrors or inside the laser, there are much higher intensities of photons in compared to the output light. Okay, so I hope this is understood, this is what it means to have an optical amplifier in terms of the picture of the uh, frequency domain. Okay. Well, sometimes, of course, you might have some gain mediums that might feed more than one resonant frequency. For example, this might be other option. You might have a gain medium which can feed not only one frequency but these two frequencies. This is also possible. Okay. In this example, that your optical amplifier is also only one resonant frequency falls under the gain, but you might have more than one resonant frequency. In that case, you might say that, okay, the output frequency or output wavelength for that laser that has this gain medium will be two frequencies, two wavelengths. It's going to be a two wavelength laser. Okay, this is possible. But you will see that if your output is more than one wavelength, this laser runs as a pulse laser. Okay, I will explain what a pulse laser is. There are two types of lasers in terms of its output wavelengths. One is a pulse laser, the other is continuous wavelength laser. A continuous wavelength laser has this example of gain that only amplifies one single mode or one single resonant frequency between the mirrors. And this is certainly, you can say that this is going to be a CW laser or continuous wavelength laser. But if your gain medium are just feeding more than one single frequency, it feeds 2, 3, 16, 50 frequencies, then you will have a pulse laser. And I will discuss how this pulse laser is pulsing with this picture. Okay, so, all right, so this is it about this picture. And roughly how the amplifier is just working. All right, so, okay, so what do you see in this picture? As I said, if you have such a gain medium that only feeds one resonant frequency in this frequency spectrum of this specific laser that has a certain distance between its mirrors, this corresponds to a uh, a driving a driven oscillator, compensating its losses by this gain. So if remember, I showed this driven oscillator uh, time domain frequency or time domain signal output. For the case of losses, this signal is just decaying exponentially. But if you drive by external sources or external driving force, your oscillator, this width of the bandwidth of the resonant frequency will get narrower because it's driven, right? There are the losses are compensated, so it will appear like this, and all other frequencies will just be removed. They will die out because they're not feed. They are not fed. There are no any light photons that are at these wavelengths anymore, at these frequencies, because they all just died out because there is no amplifier for these. There's amplifier for only that specific frequency. Okay, so eventually your spectrum will drop to this spectrum that you don't have any resonant frequencies but this one. Okay, and this one will have a very, very narrow bandwidth. Okay, so this is what happens if you put a optical amplifier inside between these two mirrors, and you go from this spectrum to that one. Okay, so you have now almost infinite wave train because there is no decay on the time domain. Okay. All right. So, I mean, this is the case for this. This corresponds to the second. We were discussing about the unique properties of the laser in our previous lectures, and this was this number two, highly collimated beam. Every laser light is very highly collimated, and it is diffraction limited. It can produce a very small focus spot. It has diffraction limited focusing and high spatial coherence. All these properties, all these properties are the result of this picture, going from this one to this one in the laser using an amplifier, and amplifies only one single frequency, and losses are compensated. So your laser will only survive for one frequency. So the light that comes out from this process will have this specific property. Okay, I mean, this picture is just the reason for that property. Okay, so uh, sometimes you will see that lasers will might have these planar mirrors, but most of the time